Okay, hello everyone. My name is Zhao. Thanks for being here for the talk. Today I'd like to invite you guys in the journey of revisiting the discovery that I made last year, researching on the topic multi-label node classification task on graph structure data. So we will journey today from definition of the problem, exploring the data set, to the intriguing discoveries that I made during the data analysis and experiments. And these observations will shed light to the limitations of the current deployment of graph neural networks, as long as the graph data set. Since most of us are working on graphs, but not everybody has background from machine learning, I will start from a broader definition of classification task in machine learning, and then we will narrow it down to the classification task on the graph structure data. So in classification tasks, what we do is basically to train a classification model that is capable of assigning labels for the input data. Here I have an example of the image classification where we input the picture of cat, and this model is supposed to see cat to this picture. But think of the pictures that we encounter every day in real life. The images are not this clean. It's more common that one picture would contain multiple objects, like this picture showing here, which contains cat and dog at the same time. In this scenario, the model is supposed to predict multiple labels at the same time for the same input data. So this is already a more complicated scenario compared to the single label scenario. And then moving from independent data like images to graphs, what we have in extra is the interconnections between the nodes. And the node classification task is where we are given a graph, its structure, the node features, and our task is to predict the labels of the unlabeled nodes in the graph. This task setting finds wide applications in real world. For example, in social networks, we know the interest of some of the users. For example, this user particularly is interested in reading, traveling, and machine learning, which sounds like many of us here today, and our task is to predict the interest of the unlabeled nodes in the social network. So after defining the problem, we see the current deployment of graph neural networks in this kind of task. What they do is basically to feed the node features and agency metrics of the graph into the graph neural networks, and then replace the softmax layer with the sigmoid layer, where we have the input as the independent probabilities assigned for each of the class. So the first limitation is already by design because the probabilities assigned for each class are independent from each other, so that the model is not capable of capturing the label correlations. And another thing that we find really intriguing is the performance of graph neural networks on multi-label graphs. So graph neural networks are verified to work really well on high homophily single label graphs in many of the previous works. And this homophily is a measurement of the similarity between the neighboring nodes. And to note that it's possible to define this similarity from many perspectives, but here in our work, we are interested in the similarity from the perspective of labels. So what does this mean in the single label graphs is that most of the connected nodes share the exact same label. Since this metric is not defined for multi-label scenario, we define in our work for the first time the homophily for multi-label graphs as a fraction of shared labels between the neighboring nodes. So here I have some of the numbers from our work. We see that from the number perspective, the multi-label graph seems to have a very low homophily, right? And would you guys assume that graph neural networks work well on this kind of data set? Exactly. And here's a $1 million question. Then would the graph neural networks designed for low homophily single label scenario work well on multi-label graphs? So to a little bit information to assist in this decision making is that what does this low homophily means for the single label graphs? What they mean is what people also refer to as the opposites attract. So the useful information is not in the direct neighborhood, but in the higher order neighborhood. Would you assume that this would work?
Still a bit on the right? I'm seeing it in the neighborhood, I've seen it in the
So the low homophily means that the direct neighbors are dissimilar. And then the dissimilar to dissimilar might be similar. So so here's the numbers that we found in our work. We choose the example from this category, model H2GCN, as an example from the models designed for low homophily single label graphs. We see that the performance is not really good because you can't even beat the simple GCN or even simpler baselines like deep work, right? But what is the reason for this? What we found in analysis of the experiment results is that the multi-label graphs have other semantics in terms of homophily compared to the single label graphs. So low homophily means in multi-label graphs that each neighbor only share a fraction of the labels with the evil node, which indicates low homophily, but we can see that the neighboring nodes are not similar. All useful information are in the neighboring nodes. And this is particularly interesting because it actually aligns with what we observe in real life. So to illustrate this, please picture each one of you here as a node in this social network. We have a lot of interests, and each of our close friends, only share one or two of these interests, which is the reason why we have these low numbers in low homophily. But can we see that we are completely disliked with our friends? No, right? Only each one of them is reflecting part of us in their interests. So the second interesting thing that we found is in the data analysis. So here we have the characteristics of ODBN proteins. This is the widely used multi-label graphs in many of the previous works. And here I have a screenshot from their website. We see that in this leaderboard, people are competing every day trying to develop more efficient models to achieve better performance on this data set and using the metric ROC AUC. But what they didn't do is trying to understand the data before they try their experiments on it. On the data analysis, what we found is that there is a huge number of unlabeled nodes in this graph. Specifically, there are over 40% of the nodes in OJBN that are without any labels. And more worrying case is that almost 90% of the test nodes have no labels. What this indicates is that the label matrix from this graph is very sparse. And combining this with long training epochs, a model that assigns negative class for each of the class is already achieving a high score in AORC. So what we do in our work is to evaluate these baseline models from 4 different metrics and combine this training procedure with early stopping to prevent these models from being overtrained. And from the perspective of AORC, we already see drops of the numbers compared to what we saw from their leaderboard. And AORC is actually the only metric that is giving us good numbers. You see the numbers that are given from other metrics, they are much lower compared to AORC. And the second characteristics of the available multi-label graphs is about label assignment distribution. Here I have the plot showing the distribution. On the x-axis is the number of labels per node. And on the y-axis is the number of nodes in this graph that has the corresponding number of labels. So we see here that in all of this work, while they use multi-label graphs, the majority of the nodes have 0 or single label. And only the small part of the nodes are multi-labeled. This is what we observe in the data set. But does this align with what we observe in real life? For example, in the dataset block catalog, the first plot shows it. In this graph, the nodes are the users, the bloggers, and the edges are their relationships, and labels are the social groups that they belong to. I challenge myself to think about a widely used social platform that the majority of the user only belong to one of the social group, and I failed. So maybe there is somewhere that we can find this kind of data set with this kind of characteristics, but at least this means that we need more diverse characteristics. of the multi-label graphs. So to address this issue, we propose in our work a synthetic multi-label graph generator model. Here I show an example of generating synthetic data set with varying feature quality and varying level of homomorphism. And there are more characteristics to play with. Please check our paper for further details. Huh?
Where is the link to the paper?
I will put it here. So in conclusion, this node classification task is still a open research field. And I'd like to invite any one of you in the audience or someone who saw this video later online, if you're looking for a cool topic to research on, this is the one. And lastly, the takeaway message for the day. We need to check the data set before we do our experiments. As researchers, we encounter everyday problems with data set. Either it's too big, too small, but the quality of the data also matters. And the second is we need to choose the right model to deploy on this data set according to the characteristics we found. And last but not least, we need to use the right evaluation metric. And I put the link of our paper here. Please check if you're interested. Thank you.
Yeah, so